Hi there, this is Mr. Jansen, and today we're looking at numbers 8 through 14 on the mid-course test. And we're going to get started with number 8. And this is just a simple linear equation that we need to solve. So remember, when we're solving equations, we have to work backwards through order of operations and undo the operations as we go. So for this one, between multiplication and addition, I have to undo the addition first by subtracting. So I subtract the 9 from each side. So when I do that, this is going to give me a 3x equals 15. And now to undo multiplying by 3, I have to divide each side by 3. So I find out that x equals 5. And that's it. So again, work backwards through order of operations and undo operations as we go. For number 9, there's two ways we can approach this. I'm going to follow the rule of thumb that says to simplify and then solve. So simplify by distributing, by combining like terms, all of that kind of stuff, and then solve. So for this one, I can distribute, so I'm going to distribute the 8. So that's going to give me an 8x minus 40 equals a negative 40. And now I'm going to add the 40 to each side. So I'm undoing order of operations. That gives me an 8x equals 0. Now I have to divide each side by 8. And when I do that, I find out that x equals 0. And that's okay. We're allowed to have 0 as an answer. The other approach to this, so if I'm working backwards through order of operations, essentially what I have here is I have multiplication and I have parentheses. And if I'm working backwards through order of operations, I would undo the multiplication first by dividing each side by 8. So here the 8s would cancel. That would give me an x minus 5 equals a negative 5. And now I undo what was in the parentheses by adding 5 to each side. So that gives me an x equals 0. So again, I get the same answer either way, and both of them are proper because I'm using distributive property in one and then working backwards through order of operations. And then the second way I did it, I'm just strictly working backwards through order of operations. But either way, my solution is x equals 0. For the next one, this is an inequality. And inequalities are solved the same way as equations are. We still work backwards through order of operations. The only thing that we have to be careful about is anytime we multiply or divide by a negative, we have to flip the inequality sign. So for this one, I'm going to start by adding the 5 to each side. So that's going to give me a negative 5 over 6y is greater than or equal to a 35. And now here a fraction is essentially just dividing by one number and multiplying by the other. And the way we undo fractions is we multiply by the reciprocal. And the reason for that is because really I'm multiplying by a negative 5/6. And if I wanted to, I could divide each side by 5/6, but that's the same thing as multiplying by the reciprocal, which is a negative 6/5. So that's what I want to do. I want to multiply each side by a negative 6/5. Multiplying by the reciprocal will cancel out the fraction. And what happens here, the 5s cancel, and the 6s cancels, and then the negative times a negative is a positive, so we're just left with y. And now what happens here, since I multiplied each side by a negative number, I have to flip the inequality sign, so that becomes a less than or equal to symbol. And over here, I just have to multiply, and I'm going to take this off to the side. Remember that 35 is the same thing as 35 over 1. And if I'm multiplying it by a negative 6 over 5. Remember that we can cross-reduce. In other words, anything in a numerator can reduce with anything in a denominator. So if I looked at the 35 and the 5, because this is multiplication, I can cross-reduce. It's almost as if I had a 35 over 5. I know that would reduce to a 7 over 1. So I can do the same thing within my fractions. I can reduce this to a 7 and a 1. And now I can multiply straight across. 7 times a negative 6 is a negative 42 over 1, which is just a negative 42. So what I end up with here is y is less than or equal to a negative 42, and that's it. For number 11, this is a compound inequality. And essentially what I'm doing here is solving two inequalities, but I'm going to do it simultaneously. I'm going to do it at the same time. In other words, if I got rid of this portion, I would solve this inequality by adding the 1 and then dividing by the 2. But if I did it the other way, if I crossed this out and just looked at this inequality, I would do the same thing. I would add 1 to each side and then divide by the 2. So rather than split this up and do this problem twice, I'm just going to treat it like I'm solving a three-sided equation. I'm going to add 1 to each side, but that includes this side and this side. So I add 1 to all three sections, all three sides of this inequality. Over here, that's going to give me a negative 4. It's going to be less than 2d, which is less than 4. And now my second step would have been to divide by 2. So I divide this side by 2. I also divide this side and this side. So I divide all three pieces by 2. That's going to give me a negative 2 is less than d, which is less than 2. And the last thing I want to do for sure with a compound inequality, I didn't do it with the last one because it didn't matter too much, but I want to graph this thing to make sure that I have a valid solution. See, this is how we check compound inequalities. It says that d is going to be greater than the negative 2, but less than the positive 2. We want to make sure that that exists. If I'm greater than the negative 2, that would be going this way. And if I'm less than the positive 2, it would be going this way. And what I'm looking for is for these two things to overlap, and they do. They overlap in between, and that's what I want with an and inequality, which is what this is. So that's a valid solution. I've checked it with my graph. I do have overlap. The thing we need to look for is if there is no overlap, then we say no solution. For the next one, it says to graph the real number solutions. So this time it's asking us for a graph, so we're going to solve it, and then we're going to graph it. So the first thing we do is subtract the 4 from each side, which leaves me with a 2x is greater than or equal to 12. And now I divide each side by 2. So I find out that x is greater than or equal to 6. But that's not what the question is asking for. It's asking for a graph. And in my graph, I know I'm going to need a 6. And you can include some other values here. I know that 0 is going to be down here somewhere. I know that 12 is going to be up here somewhere. But since it's greater than or equal to, I use a closed dot. And I shade everything that's larger than 6, which is in this direction. And that's it. For number 13, it says to solve and graph the inequality. And really, this is a compound inequality. Absolute value inequalities are really just compound inequalities. It means it's either an and inequality or an or inequality. And we always want to graph those to check our solution. So the way this works, we're going to split this into two inequalities, because that's what a compound inequality is. The first one, I'm going to write this exactly as it was written, except without the absolute value. So it's x plus 3 is greater than or equal to 7. The second equation, I'm just going to tweak this a little bit. It's still x plus 3, but instead of a positive 7, I'm going to make this a negative 7. So then instead of a greater than or equal to, I need a less than or equal to. We change the sign of what this thing what is on the opposite side of the inequality symbol, and we flip the inequality symbol. So you have to make sure you do those two things. And now I'm going to solve. Here I subtract 3 from each side. So I get x is greater than or equal to 4. Over here I subtract 3 from each side, and I find out that x is less than or equal to a negative 10. And the important thing now is to decide whether this is an and or an or inequality. And really that depends on this inequality symbol. If the absolute value is less than, it's an and. If the absolute value is greater than, it's an or. And since this is a greater than symbol, this is going to be an or. So now with an or inequality, I just graph each piece on the same number line. So I've got the negative 10 is down here. I've got 4 up here somewhere. And I know that 0 is somewhere in between. So now if I want to be less than or equal to the 4, or sorry, greater than or equal to the 4, I use a closed dot. And I go to everything that's larger than that. Less than or equal to the negative 10, I use a closed dot because the equal to condition. And I go everything to the left of the negative 10. And that's it. So I solved it and checked it with my graph. And with an or inequality, we're checking to see if there's overlap because that will change our solution. So with an and, we need overlap or it's no solution. With or, we're kind of hoping that there is no overlap or we have to change our solution. For number 14, it says write a function rule to describe the amount of change, C of x, from a $20 bill if you buy X pounds of grapes at $1.29 per pound. Okay, so essentially what we're looking at here is we need to know how much the grapes cost, and we have to subtract that amount from the $20 bill. So if the grapes are $1.29 per pound, Well, for the pounds, I'm going to call that X, so $1.29 times X. That's how much the grapes are going to cost. Okay, so this is the cost of the grapes. And I want to subtract that amount from the $20 bill because that's how much change I'll get. So that means that C of X is going to equal the 20 minus the $1.29 times the number of pounds of grapes. Okay, and that's essentially what we're looking at when we're talking about change. If we wanted this written as more of a linear equation, we would write the variable first. We'd do negative 1.29x plus 20. And I would accept either one of these answers. They're both correct, and they both give us the correct amount of change.